the floor function and the fractional part function. Two functions that are really interesting in math, and we're going to look at a lot of different problems today using both. The problems will progress from things that are like manageable to things that are more difficult. Let's actually review what these functions are. So the floor of x is the greatest integer less than or equal to x. So it's kind of like rounding down. So the floor of 4.16 is 4. The floor of 3.97 is 3. And we have to be careful with negative numbers. So the floor of something like negative 2.3 or just negative 2.3 is negative 3. Okay, the fractional part is what it sounds like. It's the fractional piece of a number, right? So for example, the fractional part of the number that we started with, 4.16, is just that 0.16 part of it. And the fractional part of 3.97 is that 97 part of it. We don't round up. Okay, a main observation relating these two that's going to be important to us for this video is that if you look at a positive integer x, or actually any integer x, the floor of it, the greatest integer less than or equal to it, is that number plus the fractional part. So you take the floor and add the fractional part, you get x back. Or in other words, you can write the fractional part in terms of the floor. It's x minus the floor of x. So today we're going to look at lots of different problems, progressing in difficulty, to see how it's interesting to deal with equations that deal with the floor and the fractional part. So we'll learn really cool tools for dealing with this, from problems that are algebraic to problems that are actually continuous. Hey, welcome to today's video on Prof. Omar. All right, so I want to start with this problem from the 1981 USAMO. So USAMO usually has really quite challenging problems, but this is a great example of dealing with understanding the definition. So on the right-hand side, we notice all the summands look like the floor of kx over k, and we're asked to bound that above the sum by n times x. Okay, so we should compare the floor of kx and kx. So kx is going to be greater than or equal to the floor of kx in general. So that gives us the inequality that the floor of kx over k is less than or equal to x. And so as a consequence, everything on the right-hand side of this inequality is actually bounded above by x itself, right? So the floor of 3x over 3 is bounded above by x, etc. And so we have n terms on the right all bounded above by x, so the entire sum is bounded above by nx. So this is an example, I know we went through it quickly, but it's an example of how to really use the definition of floor and understand what it is. So this gives us sort of an understanding of how to start. So let's look at a more complicated equation. Here we have the floor of x times the fractional part of x is 1, and then the floor of x squared minus the floor of x times the quantity 1 plus x plus 4 is 0. Okay, so this looks really complicated, but again, if we want to solve a system like this, let's write things in terms of the parts that we know. So x itself, which appears in the equation, is the floor of x plus its fractional part. So that's going to let us introduce multiple variables here and keep track of things. So the floor of x, let's let that be a, and the fractional part be b. Then the first equation tells us that ab is 1. Okay, and the second equation tells us that a squared minus a times 1 plus, and now here's the key, x can be expressed in terms of a and b, it's a plus b, plus 4 is 0. And so now we have a system of two equations and two variables that we can hope to solve. And that'll give us the floor of x and the fractional part of x. So if we look at the left-hand side of this second equation, we get the a squared and a negative a squared cancel to give us negative a minus ab plus 4 is 0. All right. But ab is 1, so we can actually represent all of this in terms of a. We get negative a minus a times the quantity 1 over a plus 4 is 0. Okay, so then we have a negative 1 contribution with the a times 1 over a. And so if we rearrange this now, we get that a has to be 3. Great. But ab is 1, so b itself is 1/3. And so that tells us what the fractional part and the floor of x are, to give us altogether that x is 3 plus a third, or 10/3. Okay, so I think the moral here is that we should take things one step at a time, represent a quantity like x in terms of the floor and the fractional part using two variables, and that helps us approach strange equations like this and at least handle the fractional part and the floor. Okay, great. So now let's take a look at this next question that is actually a continuous counterpart, and asks us to compute the integral from 0 to 1 of the fractional part of 1 over x. Okay, so again, using the floor will help us understand what this quantity is. Let's say the floor of 1 over x was an integer, n. That happens precisely when 1 over x is between n and n plus 1, but not n plus 1 itself. Okay, so if we rearrange this inequality, it'll tell us the value of x for which the floor of 1 over x is n. And it'll tell us, if we do the rearrangement, this is the same as saying 1 over n is greater than or equal to, that should say x, not 1 over x, is greater than 1 over n plus 1. Okay, so x has to be between 1 over n and 1 over n plus 1. And it can equal 1 over n, but it can't be 1 over n plus 1 if we want the floor to be 1 over x. The floor of 1 over x to be n. Okay, so in this interval, the fractional part of 1 over x is that number minus its floor, and the floor is n in that interval. So the part of the integral in that interval is the integral from 1 over n plus 1 to 1 over n of the fractional part of 1 over x, which we now have an explicit expression for in terms of x is 1 over x minus n. Okay, so we have that there. We can actually compute the integral now because we have this integral in finite bounds in terms of an actual function explicitly in terms of x. So the antiderivative of 1 over x is ln. So we get ln of 1 over n minus ln of the quantity 1 over n plus 1. And then we're subtracting n times the length of the interval. N is a constant here. So we get n over n, and then we get plus n over n plus 1. Okay, so piecing this together, the piece at the end will subtract out, so that's good. This is in terms of n. And then we'll actually bring the natural logarithms together to make things a little bit simpler here. So the fractions give you negative 1 over the quantity n plus 1. And now the question is what's going on with the logarithms? And we'll see that something interesting will happen when we look at the sum altogether, ranging over all these possible values of n. So if we take the integral from 0 to 1, the fractional part of 1 over x, or the floor of 1 over x, can range over all positive integers. So we'll have the sum from n equals 1 to infinity of the integral from 1 over n plus 1 to 1 over n of this fractional part. And we've computed this intermediate integral as being the sum from n equals 1 to infinity of this quantity that we have computed earlier right over here, ln of 1 over n minus ln of 1 over the quantity n plus 1, and then minus this 1 over n plus 1 piece. Okay, so now we've expressed our integral in terms of a sum, and that was afforded to us by breaking up this fractional part, looking at its floor, and then comparing. All right, so first let's deal with this natural logarithm part. So this can be written as by doing the reciprocal, like ln of 1 over n is the same as negative ln of n. We can write this as ln of n plus 1 minus ln of n minus 1 over n plus 1. Now if we look at the nth partial sum of this, all the ln's will cancel because it telescopes. We have ln of, say, 5 minus ln of 4, then ln of 4 minus ln of 3, etc. So the thing we're going to be left with is the ln of n plus 1 minus ln of 1, ln of 1 is 0. So we'll have ln of n plus 1 minus, and then a bunch of these contributions of these 1 over n plus 1 type fractions that we get as our partial sum. So The integral is the limit as n approaches infinity of everything in the parentheses right over here. Okay, cool. So this is actually a known sum. If we negated this quantity and added in a 1 in the sum of the fractions we'd have, we'd get gamma, which is this constant that's well known in like series type mathematics, not necessarily well known to you or I, but it's something that's out there, and it's an actual number. And so if we rearrange this, we get 1 minus that number because we have the negative of the ln is taken away, and we contribute that 1. And so this is 1 minus something approximately 0.5772. That part doesn't matter. I think the part that really matters here is in order to approach this problem, we represented the fractional part by taking pieces and looking at what the floor is, and that allowed us to deal with the fractional part by representing it as an actual explicit function in terms of x, not something that was mysterious, recognizing that it's 1 over x minus 1, minus n, when the floor of x, 1 over x, was n. Okay, so the next problem we'll look at is from the 1995 Russian Math Olympiad. And it asks us to prove that the series from k equals 1 to n squared of the fractional part of the square root of x is less than or equal to this explicit function on the right in terms of n squared minus 1 over 2. All right, so a natural way to proceed with this is inductive because the next value of n is n plus 1 squared, and then we can look at the additional fractional parts. Now we've done the computation here when n is 1. The fractional part of 1 is 0. There is no fractional part, and that's less than or equal to 0. So let's take a look at what happens when we transition from n to n plus 1. So we'll assume that this inequality holds for a general n. If you want to pause this video, try the induction yourself before we actually go through it. Okay, and so let's look at what happens for n plus 1. So for n plus 1, we're going to take the left-hand side that we have here, and we're going to add a bunch of fractional parts. They start from the square root of n squared plus 1, and then we'll add in the fractional part of the square root of n squared plus 2, and we go all the way up to the fractional part of the square root of n squared plus 2n plus 1 technically, but we'll stop at this fractional part of the square root of n squared plus 2n, because the fractional part of n squared plus 2n plus 1, that's the quantity n plus 1 all squared, is 0, because that number is n plus 1. We'll see that a little bit later. So if we look at a particular piece of this, the fractional part of the square root of n squared plus I for a fixed I, when we round down, we get n. So the square root of n squared plus I minus n is what the fractional part is. N squared plus I is between n squared and n plus 1 squared, so that's why that's the case. So what we'll do is complete the square inside of here to get an upper bound for this fractional part. If we complete the square inside, we'd be adding in the quantity I over 2n all squared. Okay, and that would give us a strict inequality, and we subtract n. So completing that square, the inside becomes the quantity n plus, let's see, it'd be I over 2n all squared, and we're taking the square root of that. So this quantity that we have as an upper bound is actually I over 2n. So the fractional part of the square root of n squared plus I is I over 2n, and that's going to happen for all these various values of I that go from 1 to 2n. So that helps us start with our sum that we have up to n squared and add in the subsequent terms and get an upper bound for the total sum. So the sum k equals 1 to n plus 1 squared of the fractional part of k, the square root of k, is going to be bounded above by, from our inductive hypothesis, n squared minus 1 all over 2. And then we add in the fractional part of all of these other terms from the fractional part of the square root of n squared plus 1 all the way to the fractional part of the square root of n squared plus 2n plus 1. By our upper bound that we just established, that should give us 1 over 2n as our first upper bound, then 2 over 2n, etc., up to 2n over 2n. Of course, we're missing the fractional part of the square root of n squared, n plus 1 all squared. That's the last term we were missing on that left-hand side, but that is 0 because that is an actual integer. Okay, great. So now we have an explicit expression for an upper bound in terms of n. So we'll get n squared minus 1 over 2, and then we have this arithmetic series that we can write in a compact form. We're summing, the numerators are summing from 1 to 2n, so we'll get 2n times, one more than that, 2n plus 1 all over 2, and we're dividing by that 2n that we have in the denominator of all these fractions. So we have n squared minus 1 over 2, and then we're adding in 2n plus 1 all over 2, and if we put that all together, we would get n squared plus 2n, which is the quantity n plus 1 squared minus 1 in the numerator. So we get an expression that looks exactly like what we wanted for our inductive step. Great, so this gives us an idea of how to actually do things where we actually explicitly find an upper bound for the fractional part by doing a completing the square type thing if we have a square root. Okay, so the last problem we're going to look at is a really interesting one, which is the question of how do you solve a quadratic like the fractional part of x squared plus the fractional part of x is 1. So I want to look at the equation the fractional part of x plus the fractional part of y is 1 in general. I'm going to make a claim that in order for this to happen, both x and y cannot be integers, but x plus y itself is going to have to be an integer. So we first make the observation that x and y can't be integers themselves, because if one of them is an integer, the fractional part is going to be 0, another one can't make up for that. Okay, so let's actually look at this equation in terms of the floor and the value of x and y themselves. So the floor of x is x minus so the fractional part of x is x minus the floor of x, and the fractional part of y is y minus the floor of y. So we get x minus the floor of x plus y minus the floor of y is 1. And if we rearrange this, this tells us that x plus y is 1 plus the floor of x plus the floor of y. Now the floor of x and the floor of y are integers, so this tells us that x plus y is forced to be an integer. So we know already x and y are not integers, and we added this necessary condition that we're forced to have x plus y be an integer. Now we'll see that that's actually a sufficient condition. So suppose x and y are not integers, and x plus y is an integer, let's call it n. Then we're going to see that we're forced to have that the fractional part of x plus the fractional part of y is 1. And that tells us the type of condition that we need in order for the fractional part of x plus the fractional part of y to be 1. Sorry, not the floors. So let's look at the fractional part of x plus the fractional part of y. Okay, so this is the fractional part of x plus, now since x plus y is n, the fractional part of n minus x. Okay, so let's represent each of these in terms of the floor. So the fractional part of x is x minus the floor of x. And the fractional part of n minus x is n minus x minus the floor of n minus x. So put these together, the x and the n minus x together give you n, and we subtract the floor of x minus the quantity floor of n minus x is the same as n plus the floor of negative x. So the n's cancel, and we're left with the negative floor of x minus the floor of negative x. And it turns out for any integer, or for any real number, negative floor of x minus the floor of negative x is always equal to 1. I'm going to let you try to figure out why that's the case, and leave your thoughts in the comments if you have an argument for why, for any real number, minus floor x minus the floor of negative x is 1. It's a cool way to think about floors, and a cool exercise for like trying to play with floors and get a sense of them in your mind. So now we have this condition that tells us when the fractional part of x plus the fractional part of y is 1. It's precisely when x and y are not integers, but their sum is an integer. And so now we can use this to go back and look at our original equation and see what we can figure out. So we have the condition that x and x squared cannot be integers, but x squared plus x has to be an integer. Let's call it n. So if x squared plus x is an integer, say n, we can actually figure out what x would have to be explicitly by realizing now we have a quadratic equation for x itself. So we turn this seeming quadratic in the fractional part of x to 1 in terms of x. We can use the quadratic formula to explicitly find out what x is. It's -1 plus or minus the square root of 1 plus 4n all over 2. Okay, so we're forced to have these two things not be integers, x and x squared, right? And we have the situation that x squared plus x is actually an integer. So if we want x to not be an integer, right now it's -1/2 plus or minus some quantity, which is the square root of 1 plus 4n all over 2. So what we need is for this to not be half an integer. So this is not something like k over 2, where k is an integer. Okay, so if that's the case, then the condition we have is that the square root of 1 plus 4n is not an integer, or in other words, 1 plus 4n is not a perfect square. Now we still have to check the situation that x squared is not an integer, and I'd like to leave that for you to solve as well, and think about, are there additional restrictions that we need in order to guarantee that x squared is also not an integer? So I'll let you finish this particular problem and leave your thoughts about it in the comments as well. So a cool introduction to the fractional part function and its weird phenomena, but cool ways to handle problems involving the fractional part that are all really different in nature.